Well, thank you very much for inviting me to this beautiful campus. This is my first time here. I probably brought the rain, but but when I go home, there'll be snow. What Joshua said was not completely true. I learned a lot from him. So I picked up research on 2D materials, when we overlapped. So UCI is one of the most active campuses on 2D research. I'm very honored to be here. And I had a very fruitful discussion with some graduate students and faculty members today. I will talk about some of our research work on controlling spins and value pseudospins in 2D materials. For the experts in the audience, please do not feel insulted. This is, I try to prepare this for up-level undergraduate students and, the beginning graduate students. And also, please feel free to ask questions if I don't do a good job explaining stuff, okay? So before the invention of all the electronic gadgets, iPad, I see a bunch here, we used to write and paint using something called lead pencil, but it's not made of lead, right? So later we know, this is made of graphite, which means to write in Greek. And the reason why we can use a lead pencil or graphite pencil to write is because when the pencil touches the pen, it leaves a bunch of debris behind. And this is the image on the optical microscope. And if you zoom in, you see stuff like this. It looks like a layered structure, right? So we now know that very well that the graphite is made of layered graphene. And the interlayer interaction is very strong. And the interaction between the layers is weak. It's something called the van der Waals interaction, right? As such, you can isolate a stable monolayer using Scotch tape. I really mean Scotch tape. And there are quite a few labs here doing Scotch tape. And this is one of the earlier pictures of mechanically exfoliated monolayer graphene on silicon substrate. And the reason why you can see it because of optical interference, on silicon and silicon dioxide substrate. And because of this saturated bonding of this monolayer, you can also come up with a lot of chemical methods to grow those materials, So here shows chemical vapor deposition of a monolayer of graphene metallic substrate. So graphene is very unique, and the story has already been shown by those two gentlemen, and they got the Nobel Prize for their groundbreaking experiments regarding the 2D material graphene. And a lot of interesting physical properties actually emerge because of the linear dispersion. I mean, the energy versus momentum in this linear shape near the Fermi level, where low energy physics matters. So at the time, so when I visited again Columbia, when I spent a year with Joshua and Professor Tony Hines was like around 29, So the question at the time is like, is the 2D business over? And actually, it's just the beginning of it. It turns out that there are many, many materials that share similar structure as graphene. And I have the periodic table, and I'm showing something made of 2-element compounds, and there are many more if you use 3 elements or 4. Okay, so graphene is sitting here, and the boron nitride is very similar to graphene. And then you can have a group 3, group 4 chalcogenides, and the topological insulator, research going on in this department. This is also layer structure. I'm going to talk about most today is on the transition metal chalcogenides made of like a moly tungsten with sulfide selenium. And there's also this transition metal trihalides, chromium iodide or whatever, bromide. So this is like a new class of metallic material. And as you can already see from this picture that there are many different physical phenomena going on. You can have semiconductor, semi-metal, metal, or superconductor, charge density wave, or magnetism. So it covers a very wide range of physics. So why should we be interested in two-dimensional materials? And this question probably has been asked quite a lot. And I have just a very simple table to show that this is something interesting from both physics point of view and maybe technological application point of view. So quite a few of them, they show unique properties that do not exist in the bulk limit. And once you get down to one sheet or two sheets of atomic membranes, the interaction effect, the Coulomb interaction becomes very strong because you can imagine lots of field lines sort of live in vacuum or determined by the environment. So you can have very strong Coulomb interaction, and that gives you interesting interaction effects. Mechanically, they are very strong, So for example, graphene, this is a picture from my colleague, Paul McQueen, so they are using the traditional, applying the traditional Japanese paper cutting, folding tricks to graphene. So this is single layer of graphene. You can stretch it, you can, form all sorts of shape. So you can think about using them as flexible membranes, and because they're only one layer thick or a few layers thick, you can perturb the system easily. You can either put charge into it or do something or change the environment. So doing those things can change the physical properties. And the last point, second to last point, they're very easy to be integrated with other systems. So other devices or material already existing, let's say, and you can add this as an additional functionality. So my last point, but perhaps the most important point at this point, is that now because the layers do not have dangling bonds, so you can easily stack them on top of each other or do something to sort of design new materials that do not exist in nature. So this is kind of atomic sandwich painted by those guys in their review paper. And this is how you can do it. And many of the quite a few labs here, they have this technology. So if you are interested, you can try to visit their lab. So what's happening here is that you have some kind of a polymer, and then you have those single sheets, whatever, living on some substrate you already identify. And then you come in with stamp, you can pick it up because the adhesion to the polymer is stronger than adhesion to your substrate. And adhesion between your 2D material and your stamp can be changed by changing the temperature of that stamp. So you can pick it up or drop it, put it pretty much everywhere you want, anywhere you want. And with very high precision, we can control the position within micron, for example, and the relative angle between different layers within 0.1 degree, So, and the interface, actually is very, very clean. And a lot of new physics has already been observed in this kind of system. Okay, so after this short introduction, I would like to get to the topic today. So this 2D research is a very large field. Today, I would like to discuss this particular topic of new quantum degree of freedom in one set of these 2D materials and how we can control this degree of freedom. And I first talk about how to control it using current, and then talk about how to do it using electrical field or voltage. And this has some implication for spintronic devices. Okay, so what is valley? So I'm showing here is an example, well-known example from solid-state textbook, silicon, for example. So it's a diamond structure, right? And this is the Fourier transform, is in the first Brillouin zone of silicon. And if you look at the conduction band, actually there are 6 pockets, those guys, and they're degenerate. So they are the energy minimum, and that's the degree of freedom we are talking about. So those are the energy maximum or minimum in the momentum space. So like other well-known degrees of freedom for electron, for example, charge or spin, they could be used for information processing or to carry information. So if we want to pursue something like this, we ask ourselves a lot of questions, what is the lifetime? What is the coherence time? How can you control the valley degrees of freedom, right? So why we don't just use silicon or, aluminum arsenide, something we already know. One of the difficulties is to control this degree of freedom. And in the lab, we have the knob of electrical field, the magnetic field, those are light, those are very convenient knobs to tune. But in this system, it's much, much harder. You can apply pressure or do something, deform the crystal to sort of adjust or control those valleys. So it turns out that this class of material, we now call them transition metal, 2-dimensional transition metal that are called charging-nice, moly sulfide, molybdenum sulfide, whatever, it carried this, it does have this degree of freedom, okay? So let's just take a look at the atomic structure. So this has a trigonal prismatic structure. So the transition metal is sitting in the middle, and it has 3 sulfide or selenium on top, and another 3 at the bottom. So this is like a side view, just, yeah. And if you look from the top, then those 2 sulfide atoms are sitting on top of each other. And then you have this molybdenum and the 2 sulfur and so forth, so forth. So this looks pretty much just like a graphene, right? And the difference is that now this A and the B sublattice now are made of different atoms. So you break the AB sublattice symmetry, just by putting different elements. And that has a strong consequence. And also, if you look from the side, and you can see this guy does not have any center of inversion. So this is non-central symmetric. And that will also give you lots of interesting electronic or optical properties. Okay, so like a graphene, so if you look at the Brillouin zone, so this is the first Brillouin zone, it turns out that the energy minimum and the maximum, the gap, sits not at the gamma point, like a gallium arsenide and other conventional semiconductors. it occurs at those corners, the 6 corners. Well, I should call it, this is like 1/3 of a corner. This is 1/3. So you have K and the K prime, K prime, So 2 different types, K point and the K prime point. So this is like a simplified version of the electronic band structure. Okay, so now we have direct band gap and at 2 different values. So we have something sort of similar to spin, the 2 states. But in order to address them, we need some physical quantities. And in this system, there are 2 physical quantities that are different for the 2 values, for K and K prime. So the first is the orbital magnetic moment. So I just want to give you this kind of a pictorial view of K and K prime. So a simple way to think about the electron residing in the K valley, you can think of the wave packet and it's self-rotating. In the case of K valley, you can think of this wave packet rotating in clockwise direction, and for the other valley, it's counterclockwise. Okay. So if you accept this picture, you can easily convince yourself that this orbiting gives you magnetic moment, and this picture and that picture give you 2 different magnetic moments. One is this way, and the other one is into the plane. So now we have the orbital magnetic moment. You can address or distinguish the 2 by using, for example, outer plane magnetic field, right? And this has been observed experimentally. And the other kind of important consequence of the orbital magnetic moment, valley contrasting orbital magnetic moment, is a coupling to light. You can easily imagine that for something like this, it's easier to couple light with the same polarization. So this valley couples to right-handed light, and this valley couples to the left-handed light. And this is a very, very convenient way to inject or probe the different valleys. So the valley contrast orbital magnetic moment gives us distinct optical selection rule and also the Zeeman effect. Okay. The next important valley contrast quantity is something called Barry phase, Barry curvature, and we have heard this quite a lot. And I don't know whether I can explain this in a couple of minutes, but I want to show you maybe some pictorial thing. It's not rigorous, okay? So let's think about, moving around in some space, okay? So I'm just showing here is, let's say, I start from point 1, and it goes through some path and come back to point 1, right? So if I just have a single point and I move around, I go back to the original place, I have the same state, right? However, if I have something else associated to my point, so in this case, it's a direction, it's an arrow, right? And I move my point slowly, and every point I make sure that the arrow is tangential to my surface. Then after completing a closed path, when I move back to the original point, the arrows are at 2 different angles, right? So now I do not recover the original state, right? So this is a geometrical effect, right? And in quantum mechanics, so this is completely classical, right? So in quantum mechanics, we have seen something very, very similar, right? So for example, in the Aharonov-Bohr effect, so we have infinite long solenoid, and you have current going, right? Magnetic field is pretty much confined inside the tube, outside nothing. But if you move electron, make a closed path around the sky, although there is no magnetic field, right? You're going to pick up a geometric phase, and that phase is determined by the magnetic flux, right? So this is something well known in quantum mechanics. So I can make an analogy in the momentum space. So this is real space, and this is momentum space. So let me describe my electron, block electron in a solid as this plane wave function and this periodic part, right? So if I move slowly varying my wave function along k in momentum, right? If I go through one Boolean zone, I sort of make a circle, right? So in that case, I also pick up a phase, which is the integration or the magnetic flux when I integrate in the momentum space, right? So this guy is called the Berry curvature. And by construction, you can see this is fully equivalent. Oh, no power, sorry. No, I don't need you. I just, sorry. Okay, so this is equivalent to this B, right? So you can think of, and then you can, this is determined by the topology of your band, right? So we can see here the Berry curvature is some kind of a magnetic field in the momentum space, right? But, we sort of ignore this most of the time, and there's a good reason why we do that. So the Berry curvature is like a magnetic field, so it's a pseudo vector, right? So it transforms like a magnetic field, right? Pseudo vector. So if I do spatial inversion operation, this does not change, right? And if I do time reversal operation, you gain a negative sign. Therefore, if I have both spatial inversion and a time reversal inversion symmetry in the system, then I should get the 0, right? So in order to get the non-zero Berry curvature, I need to break one of those. And luckily, in the system, I told you there is no inversion center for monolayer moly sulfide, for example, showing in this picture. So because of that, there is non-zero Berry curvature somewhere in the electronic band, right? And luckily for this system, that maximum of Berry curvature happens at the K and the K prime point, where interesting physics happens. Electron sits there. So this is kind of important. It's kind of a lucky consequence, okay? Okay, so just, to summarize what I said. So this is the intrinsic band property. If you have the right symmetry, you will have it. And for two-dimensional materials, Berry curvature is out of plane. And you can think of this as magnetic field in the momentum space. And there have been experiments showing that this is not imagination. This is something real, okay? Okay, so one of kind of important experiment to show that the Berry curvature is really a real physical quantity in this system is the Valley-Hall effect. So we said the Berry curvature is like effective magnetic field, right? So if you drive currents, then the electrons will experience this anomalous velocity because you have this magnetic field there, right? So it should bend its trajectory. And in this case, if you have equal population of K and K prime, or negative K is the same thing, electrons, one type of electron will be bent towards one direction, and the other will be bent towards the other direction, right? Because they have different sign for the barrier curvature. So this effect has been predicted, and in 2014, the Cornell group actually experimentally demonstrated this. And the way they did it, they constructed kind of a regular Hall device. So they have like a full contacts, you drive current along one direction and try to detect Hall voltage in the perpendicular direction. So for the effect we discussed, right, we don't have anything to differentiate different flavors of electrons. So if you just detect Hall voltage, this should give you 0, right? So the trick those guys played is to use the optical selection rule I mentioned before. So they pump this system using circular polarized light of a well-defined handedness. So in this case, you're going to break the balance between K and the K prime electrons. And that way, because of the anomalous velocity, you will be able to pick up Hall voltage when you bias it. And this is the evidence, So this is the one handedness of light, and this is the other handedness of light. And if you use linear polarized polarization, which is 50% this, 50% of that, you get the 0 effect. So that was kind of a first experimental proof of this Valley Hall effect. So in 2016, we pick up this problem again. So what we would like to do is to directly image the effect and try to study a little bit more of the transport of the electrons with different Valley flavor. Okay. So this is kind of the experimental setup. We have electrodes, and we have monolayer of moly sulfide, and then we can drive current, right? And if there is Valley Hall effect, you should have Valley current across. Just means one type of electron goes one way, another type goes another way. And then we use optics. So in this case, it's a co-rotation microscopy. So coming with linear polarized light, and if there's accumulation of Valley at the edges, the Fermi level between the two valleys will be different, right? And then, if you come in with optical probe, sort of close to the Fermi levels, then this absorption and this absorption will be different. And as a result, the refractive light will have rotated a different polarization, and optically we can pick up the signal, and then we can scan through the whole sample and see whether there's any effect. So here's the result. So this is the sample we studied, so gold electrodes, monolayer of moly sulfide, and shape it into this rectangular shape. And we can run current this way. And this is the co-rotation image. So this is the electrodes, and this is the electrodes. And you see opposite sign of co-rotation. So red for one type of flavor of electron, and the blue is for the other type. And then if you can analyze, if you have the resolution, you can analyze what's happening at the edges. You can extract things like what is the mean free path of the value pseudospin, things like that. So okay. So by playing with symmetry, you can also control this effect. So let's take a look at a bilayer. So a bilayer, in this case, natural bilayer, is just you take one layer and you have another layer rotated by 180 degrees and sitting on top of each other, right? So if you look at this, definitely you can find a center of inversion. It's sitting right here. So this system, from the symmetry point of view, we know that Berry curvature should be 0. So you do not expect to see any very, very Hall effect. However, if you can break the symmetry, then you should see it, right? So we have a control knob, right? And in this case, it's an out-of-plane electric field. So if you do that, you break inversion symmetry this way or that way, so you should see a different effect. So let me quickly go to the result. So this is kind of the result. So in the case when we don't apply any electrical field, the signal is relatively weak. But if you apply electrical field in one direction, you see red here, blue here. And if you switch the direction of electrical field, you see blue here and red here, right? So sort of consistent with our expectation, roughly works. But you may ask me, so if you look very closely here and there, it's not very clean. What's going on right in the middle? Something else is happening, right? So we dig into this problem a little bit more, and we come up with, with different guesses. One of the guesses is that maybe the samples, when we try to make the device, they are not uniform. And for a control, we made a stringed uniaxially, string the sample, do the test. And this is kind of an interesting result you can see. So we string this and do the same experiment. You run current one way or flip the current. Now you see that, this is the electrodes. Maybe you have something at the edges, but like what's more visible here now is that the whole sample light up on the optical curve rotation microscope. And remember, what we are measuring is magnetization, right? So now we can run current this way. We magnetize the whole thing red, and we flip the current direction. We get flipped magnetization. So what's going on here? Before we address what's going on, we did a little bit of study on the dependence of the effect on the direction of current. Okay, so we made this a Corbino disk type of device. So the dashed lines are electrodes. So we have a middle electrode, and we have electrodes on the side. So in this kind of a device structure, for most angles, we have diagonal current going on, right? So this is sort of uniform current, supposed to be. And then we make a stringed monolayer molysulfide, and we put on these electrodes. And this is what we saw. We saw that there's one line that almost no signal. And on one side, we have positive magnetization. On the other side, we have negative magnetization. And this is for the sample stringed in other direction along crystallographic axis, different crystallographic axis. And always there's one line, almost no signal, and one side is blue, one side is red. Okay. So what is this special line? Okay. So this line, we know what that is because when we string the sample, we first did nonlinear optical measurement. I'm not going to get into detail, but this technique tells us the crystallographic orientation, whether it's armature or zigzag. So we know which direction we pull the membrane. And this direction is always along moly and sulfide. Okay, so this line is always along this Okay, and this is a kind of a simulation to mimic, this experiment. So it looks like this direction is kind of a special, and this is kind of a lipid ionic crystal, right? So if you deviate the ions from their equilibrium position, you can generate, if not piezoelectric field, but some kind of polarization, right? So I use this as E. And when you run current, you have the magnetization, which goes like a product of the two, cross product of the two. And this is out of plane, okay? So, so this tells us something. And so we think, so this is, it's the string sort of creates this polarization or electric field. And once you run current, you generate some kind of magnetic field, effective magnetic field, which pings the orbital magnetic moment this way or other way, determined by this relationship. And for those of you who are sort of interested in the microscopic picture of this, there is a kind of a nice News and Views article about our work. So what's happening here microscopically is the following. When you string your crystal, I'm talking about moderate string. So in most experiments on the order of 0.5%, okay? You're going to move the K and K prime of your honeycomb. Well, you change the honeycomb shape, right? Equivalently, in the momentum space, K and K prime value will be shifted away from their original position, either away from each other or closer to each other, depending which way you stretch, right? And they have to go like an opposite direction because the system has time reversal symmetry. So this is to respect time reversal symmetry. But the Berry curvature dipole, or Berry curvature as a function of momentum can also be changed, but they don't move together with band minimum or maximum, okay? So they are sort of not move together. So if you run current, and what happens to the Fermi level is that if you don't talk between the two different valleys, then in each valley you are going to have a tilt of Fermi surface. So you have a little bit more electrons here and a little less here. So now if you do your averaging, the positive magnetic moment you integrate over one valley cannot completely cancel the negative magnetic moment you integrate over the other valley. Therefore, you will get non-zero magnetization over the entire sample. And then you can reverse it using current. And this effect can be much, much bigger, at least from our experiment, than the intrinsic valley Hall effect. Okay, so I talk about how to generate a valley magnetization either on the edges by the valley Hall effect or throughout the channel using this stringed sample. We call it magnetoelectric effect. But is there any way to control the valley magnetization without current by pure electric field or voltage? And this is kind of important because you can reduce power consumption, you can speed up the device significantly. So this is kind of the ideal structure we would like to have. So let's say you have some active medium sitting in the middle, and you just want to have a capacitor, and turning on and off, you want to switch the magnetization. So this is kind of what we'd like to have. And this is not a new idea, and the idea has been exploited using dilute magnetic semiconductors in ferroelectrics, the oxide materials. There's some success, but not, there are many limitations. So we would like to see whether the 2D materials are good for this. And one thing they are good for this because I talk about 1 layer or 2 layer, it's relatively thin. So the electrical field effect should be more effective because you wouldn't have a lot of screening, so you can control it more efficiently. So that's kind of the motivation. So let me just go through the basic requirement for controlling magnetism using electric field. Okay, so I'm showing here is the free energy as a function of electric field and magnetic field, and those are the terms we usually see, right? If there is a coupling between the electric and magnetic fields, in the leading order term, you can just write down something like a proportional to the product of the two, right? So this is the linear magneto-electric effect, right? So to find a polarization, I take a partial derivative of the free energy with respect to the electric field, right? So I can get some term proportional to the magnetic field, right? Similarly, I can find a magnetization as partial derivative of this guy with respect to the magnetic field, and I get a term that's linearly proportional to the electric field. So just by the construction, P equals to some constant times magnetic field, right? In order to have this, you need to break inversion symmetry, right? If you have inversion, this guy changes sign, but this doesn't, so this alpha is 0 if you have inversion symmetry. And in order to have this, you need to break time reversal symmetry. So in order to have linear magneto-electric effect, this term, you need to break both inversion and the time reversal symmetry. And the example I showed you in the stringed monolayer moly sulfide, we apply current or apply field, we saw magnetization, right? Inversion symmetry is already broken in that system. It has, non-central symmetric atomic structure. And the time reversal symmetry in that case is broken by the current. You have dissipation, once you run current, you break this. So based on this analysis, if you want to have something like this without involving current, I need to break a time reversal symmetry. So I need some system that, has no time reversal. And magnets will be a very, straightforward candidate. So recently, Xiaodong Xu's group at Washington with Pavlov's, the MIT group reported this chromium triiodide being ferromagnetic down to monolayer thickness. And this is a semiconductor. And the way why it's kind of magnetic is you can think of the chromium gives 3 electrons to iodine, and then you have 3 remaining, and because of the crystal field, e.g., those 2 levels split, and then the 3 electrons live here, and they line up. So this is ferromagnetic, and the spins in this case are out of plane. So you can think of it as 2-dimensional Ising, and they live in honeycomb, okay? And this system itself is interesting, okay, by itself. So let's look at the interaction strength, okay? So bulk chromium iodine has a Curie temperature about 60 Kelvin. And then if you convert that to energy, that means the interlayer coupling is on the order of a few millieV, right? And we have done, and the original paper also has shown that this material shows a very interesting layer-dependent magnetic order. So in the monolayer, if you look at magnetization as a function of magnetic field loop, it shows very nice hysteresis loop. It's a ferromagnet. However, if you go to 2 layers, magnetization disappears. And later we learned that it's because in 2 layers, the layers couple antiferromagnetically. So the spins either like this or like that. So they cancel. So it has a very interesting layer-dependent magnetic order. Okay. So, but to take something out of this measurement is when you look at the field at which spins flip, the spin flip transition. Okay, when the layers flip, it occurs at somewhere around half Tesla, and you can convert that to energy too. So we have this bilayer system with very interesting energy scales. So within layer, the energy, interaction energy, is on the order of a few millieV, and between the layers, it's a fifth of millieV. So this is much, much weaker than that, and also on the absolute scale, for a lot of experiments, this is very small energy. So that suggests that you can do a lot of things to change this, perhaps change from this alignment to that alignment. Right? Okay, so, and we are interested in using electric field to flip the spin, the magnetic order. Okay, so let's take a look at the symmetry, see whether this makes any sense. Okay, so I'm showing 2 layers of chromium iodide, and I took away the arrow for the spin. Let's now look at the spin first. So if you look at the monolayer structure, you can clearly find the inversion center here, right? So the structure itself is centrosymmetric. And that applies to 1 layer, 2 layer, 3 layer, throughout the bulk. If we are looking at ferromagnetic, when the spins line up, it has inversion symmetry. But if you look at antiferromagnetic states, this has broken inversion symmetry if you take the spins into account. So based on this symmetry, we expect no linear magnetoelectric effect in monolayer, not either in 2 layers of ferromagnetic coupled bilayers, but in the antiferromagnetic coupled bilayers, we do expect to see magnetoelectric effect. So let's see how it works. Let me first show you experimentally how we do it, right? So I showed you the capacitor structure. Basically, this is the capacitor structure. So we have this magnet sitting in the middle, and we have boron nitride as dielectric, gate dielectric, and we have graphite, as gate. So you can apply top gate or back gate, and you can adjust the voltage on those. So we have 2 degrees of freedom, and you can do 2 things independently. One is to change electric field perpendicular to the material, and another one is to change how many carriers I will flow into the channel, right? So you can change electric field and electrostatic doping independently. And the numbers, for the field and for the doping actually can be quite significant because we are working with a few nanometer thick gate dielectrics. Okay, so let's do a quick check. So this is the effect for monolayer chromium iodide under half volt per nanometer. That's not a small field, that's pretty big. But you can see that the loop sort of pretty much sitting on top of each other. So the effect is very small. And that agrees with our symmetry analysis. However, if you look at the bilayer, so this is the case when you don't have any electric field, and when you apply electric field, suddenly you see the loop opens up. So now you have non-zero magnetization, and then if you apply a large field, this loop opens up more. And then if you look at how large this is as a function of electric field, it goes linear, okay? And that's for the antiferromagnetic region. And if you go here, ferromagnetic, and that's this guy, it's much, much smaller, and it's not linear. So there are some higher order effects, but there is no linear magnetoelectric effect. So this is fully consistent with our analysis. One thing I would like to mention is that if you look at this slope, this tells you how strong the effect is, right? And this coefficient actually turns out to be very large. And this is one of the largest coefficients we know in different materials, okay? And it turns out that there are more efficient ways to control or switch the magnetism. So what I'm showing here is what happens when you put in more electrons and more holes into the system. And you can see here, this loop shrinks, and at some point, it almost goes to ferromagnetic phase just by putting doping. And this is sort of very interesting. And one thing, one can sort of show is that you can switch it using now voltage, right, gate voltage. We cannot do it under zero magnetic field yet. So this is under a bias magnetic field. So if you look at, for example, at this magnetic field, right? So for this electric field, it's in the ferromagnetic state. And for this electric field, it's in the transition, right? And for this, you're in the antiferromagnetic state. So if I park my magnetic field right here and I switch, dial my gate potential, then I can switch the system from high magnetization to low, high to low, right? And this is what this shows. We don't have a number yet about how fast we can switch this. The answer is pretty fast. So hopefully soon we'll have an answer, like whether this is gigahertz or megahertz. Okay. Okay, I switched this. So I think I need to finish. So I want to close the loop. So I talk about controlling the valley magnetization in molysulfide or in those transition metal that are chalcogenides. I talk about using gate voltage to switch magnetization in bilayer chromium triiodide. So what we would like to do is to make some kind of ferromagnetic semiconductor out of those guys, and you can also electrically switch. Okay? And one idea is to, for example, I put this guy next to the magnet, and if they talk to each other, and if I can switch the magnet, then I should be able to switch the valley magnetization in this material. So that's kind of our naive idea. Okay? So if you can do this, how do you know you have already done it? We can watch the photoluminescence, because I told you about the optical selection rule. If it's in the out of, this way, magnetization, it should emit one type of circular polarization light. If you go to the other magnetization direction, the polarization of emitted light should change, okay? So we made such device, and here is the result, okay? And this is something you've already seen, magnetization of the magnets as function of magnetic field, right? When we sweep the magnetic field, we are switching the magnet, right? And what I'm showing here actually is the handiness of the photoluminescence from the semiconductor sitting next to it. And you can see it that the light polarization changes from one handiness to another handiness when I try to switch magnet. And this is the same thing when I flip the direction of my magnetic field. And if I plot the handiness degree as a function of magnetic field, I also get this nice hysteresis loop, which follows that guy. So it seems that it works. And then you can also try to use gate voltage to switch from one handiness to another. So we have turned a non-magnetic semiconductor to a magnetic semiconductor by putting it next to a magnet and electrically switch the magnetic order. So I would like to finish my talk by posting this question, So you can sort of play a lot with this kind of a system, but kind of a interesting question to ask, what is the microscopic mechanism, when you apply electric field, why it changes the magnetization or magnetic order even, and when you put in doping, why the magnetic order changes, and how does another layer of a semiconductor talk to that layer of a magnetic insulator. So those are open questions, and we've just scratched the surface of this class of material. So I'm not going to propose some scenario, but so this is an interesting kind of area to explore, try to understand a little bit more of this exchange or super exchange interaction. Okay, to summarize, so I mainly talk about the value degree of freedom in two-dimensional transition metal that chalcogenize, monolayer of moly sulfide, tungsten selenide, and the two valley contrasting physical quantities, the orbital magnetic moment and the barrier curvature are extremely important. Because of those two, we can sort of address the value degree of freedom by light, by magnetic field, by electric field, right? And I've shown you how to generate them using current, and I also talk about how to electrically control them through controlling the magnets. Okay, so last, and I would like to, but not least, okay, to give credit to those who did the work. So Professor Kim Fan Mak and I co-supervise the group. So this is our joint group from a few years, maybe 2 or 3 years ago. So the Valley Hall effect was led by this former postdoc, Ji-Young Lee, who is assistant professor in Korea now. And the electrical switching of magnets was led by another postdoc, Shenwei Jiang. And the coupling between magnets and the semiconductor was done by a new graduate student, Li Zhong Li. Thank you very much for your attention.
One question about the magneto-electric effect in the bilayer
Yeah.
You have both the positive and negative signs. So how do I understand the sign?
Okay. So there are two different states of antiferromagnet. So one is like this. Another one is like that. So depending on the direction, you get two different signs. So one state give you one sign, the other state give you another. Oh, okay. So we can do, magnetoelectric cooling, things like that. We can cool down the sample, so you prepare the states in that way. So you can apply electric field while you cool down, or apply magnetic field when you cool down. So you pick one state.
But you can't pick this versus this, right?
So if you don't do anything, you cannot. They just occur like that. But before you cool down, you can first apply electric field and magnetic field, and then you cool down. And that will pin down like which state you're. So from that hysteresis loop. Yeah. So for example, this picture, right? So we always know like which direction magnetic field we apply, right? So we know like at this state, all spins line up like that. Right, and if you start from this state, which.
In the middle, right? Here.
Yeah.
Let's say if over here, you have when you rub down the magnetic field, your right is positive.
Mm-hmm.
So does that mean if I go to say this electric field, when I rub down the magnetic field, those two curves basically just merge, and then essentially the right goes to negative, then the black goes to positive?
No.
So if I look down here, right?
No. So this is already you flip the electric field direction.
I flip the electric field direction.
Yeah.
Do I also flip the moment there? I mean, your magnetic contrast.
Okay. So this depends on history, how you cool down, which way you come. So that's we can talk a little bit more about how to get to this. So the key is magnetoelectric cooling. You cool it under the fields. That's what we do.
Regarding this, in order in the string, moving sulfide phase, right? Do you see a TC, Curie temperature, like the critical temperature is ferromagnetic?
Oh, okay. No. This is generated by current. No. So.
The question is like how they order, or is ordered by external.
So this is driven by current. Once current is gone, there's no magnetization, and this effect survives at room temperature, and it can be made pretty big. And we have studied other systems that can give you even bigger effect. And then this magnetization, you can also probe it using transport. For example, we have seen nonlinear anomalous Hall effect, by doing transport. It's the same type of physics. So you have magnetization when you generate by current, but at the same time, the current is going to feel this magnetization, and then you're going to have Hall voltage, although the system does not break time reversal symmetry itself,
How to understand the change of exchange coupling between layers by electric field or doping?
This is a tough question. So I propose one. Okay. So what I'm showing here can give you an answer why in the middle the magnetization becomes non-zero. So for example, if the electrical field can induce charge transfer, which is quite possible, right? Because under electrical field, the two layers will have different potential. So then you can have charge transfer. And if you transfer carriers from this layer to this layer, then because of the exchange, the spin has to flip to keep the energy low. So you get, upspin. So that way you will get non-zero net magnetization. But this is like one possibility. But what's kind of more possible maybe is that there have been some numerical studies of, so first of all, why bilayer is an antiferromagnet maybe is a deeper question to ask. In bulk, they all line up, and in bilayer, suddenly they prefer this ground state, right? And there have been a few numerical studies, So because the energy scale is so small, I showed you, right? It's like a 0.2 millieV. So if you shift the two layers, this will have a large effect on the interlayer coupling. And whether it's like which atom is sitting on top of which can be very important. That's one thing. And that can also have another consequence. The distance between the layers can also be slightly different depending on who is sitting on who, right? And that can tip your magnetic order this way or that way. So quite a lot of unknowns, yeah.
So your very polarized electrons travel over microns, several microns distance. I was wondering how high temperature does it affect it?
So let me make it clear. The current, valley polarized current goes through this whole channel, but the mean free path is very short. Actually, we have not been able to optically resolve this yet. So what's happening is that the K electron goes this way, K prime goes that way, right? And when they reach the boundary or some impurity or defects, they scatter with that boundary. And then you have accumulation. Because when you have current going, it's like a pump. So you keep pumping, and at the edge, they just scatter. And over time, it's kind of a quasi-equilibrium sort of, you reach some kind of density over there. And in order to see the kind of the scattering length of valley, we need to look at very close to the edge, see how the signal goes down when you move away from the edge. And that length will give you the valley scattering length. And with 1 micron, half micron, we have not been able to see it. So it's probably shorter than that. And the highest temperature we have seen this is 100-something Kelvin. Yes?
What's the strength of the magnetic field that you have to use to bias for the switching?
Like half Tesla or something, in order to see it very clear switching. That's not good.
So you can't see it if you just put a small field?
No. So right now, it is because right now we rely on, see how the spin flip transition field changes with the gate voltage, right? So something like this, I can use much smaller bias magnetic field to switch. But if this loop, this width is still large, then I cannot. Yeah. So this can be, still a fraction of Tesla. It's big.
Can you explain a little more about the difference between field and doping?
Oh, okay. I don't know why, to be honest. So microscopic picture, right? So one possibility why doping is more effective in controlling the magnetic order is, it all depends on those calculations, see which one. So let's say you're putting more doping, it can change the layer separation, to minimize energy, and that will give you a huge effect, for example. And yeah, so no clear answer. More studies.
Technical question.
Uh-huh.
In the previous string monitor itself,
Yeah.
how did you string the sample?
Okay. So in the experiment I showed you, it's a very low-tech technique. Okay. So we put the sample on polymer, stretchable, and then you string it, but you cannot string it too much, otherwise they're going to slip. Okay. So then you deposit on your substrate which you want to measure, and you hope that the string does not relax. But luckily, we have optical techniques that can monitor the amount of string. So we know which device has string, which doesn't. So that's kind of the first generation. And the next generation, our former postdoc workout is to use this very standard flexible electronic substrate. What's the name of this? Yes, yeah. So she made devices on this flexible, substrate, and then when you bend this polymer, you see it, and you can bend it. You can make it flat, and you can change it. And then one more version we made is to suspend the whole device on a trench. We dig a trench and put on it, and then we use the backgate using electrostatic force to pull the membrane down to apply strain. But in that case, the string is not uniform.